This is for the 4.9 notes. It does start off with this thing called a launch, which is kind of helping us think about what we did yesterday with using congruent triangles. Like first we had to prove them congruent to each other, then we decide, what is it that we need to show. A lot of it we did yesterday with saying, okay, what else is true about these triangles, and then kind of using that to pivot off of it. Well, we can do the same thing today. Instead of doing all three of these proofs, because they're all about 6 to 7 steps long, and they're actually all theorems that we're about to see on the next page, where we're not going to really use these in proofs as much until tomorrow, but today we're just kind of learning about them and then applying them to problems. So here's what the first one says. We want to make sure we at least just understand the diagrams, but we don't need to know how to do the entire proof, because this is, again, proving the different theorems. This first one says that line CP is perpendicular to segment AB, and then we know already that segment AP is congruent to segment BP. So it does show me perpendicular, which means I don't quite have a right angle just yet. I'm going to need to show that in my proof, but this is actually, the theorem is called the perpendicular bisector theorem, and we're about to see it on the next page, and the actual words that are written out for it, because we're going to try to prove that AC is equal to BC. So if you're noticing this segment and this segment being equal to each other, not just congruent, but equals. That's why if you were to do this proof, it ends up being almost 7 steps, because you end up having to work with congruence and then having to switch it back to equals at the very end. So we'll see, what does the perpendicular bisector theorem tell us on the next page, because yes, we are going to show, just to kind of give you a little outline of what to expect here. You are going to first show that, if perpendicular, then right angles, right? Because we have these right angle symbols that will show up. And then if right angles, then we want to show that the angles are actually congruent. You're also going to see reflexive, right? We see a reflexive property. So this is going to be an SAS. If we were to do the entire proof, instead, just kind of outlining it so that we can have an overview and not spend so much time on just this, because today's also a shorter hour. So SAS gives me how the triangles are congruent, and then remember that we can show something else is true based on that theorem from yesterday that says if triangles congruent, then their corresponding parts are congruent. So the part I would show that's congruent, or what I want to show, is this. I would show here that CA is congruent to CB, right? So in the orange here, I would have to need to show that segment AC is congruent to segment BC once I know the triangles are congruent, and then I could then just convert it to equals. Convert to equals. Okay, so that's kind of the plan here. If you decide you want to try this proof for some extra practice, you can absolutely do that. For right now, we're not going to spend more time on that, and that's kind of what the perpendicular bisector theorem tells us. That here's what it says in words. It says if there's a point on the perpendicular bisector, then the point would have to be equidistant. Equidistant means the same distance away from the endpoints of the segment. And so if that seems too wordy, I know that it does, and this is what's on your yellow sheet. I'll show you where that is on the next page. We're going to eventually use this on proofs, not today yet. Homework on the proofs that you have on homework, don't use this theorem just yet, because we do need more practice with it. So the idea here it's saying is that if there's a point on the perpendicular bisector, so remember CP is the perpendicular bisector, so if C is a point, or maybe I want to add in another point and call it D, or I want to add in another point and call it something else. Any point I put on here on this line is going to be equidistant to the endpoints of the segment. So if I want to draw D to A and D to B, these would also be congruent, therefore equal. And that's what this is saying. It's saying equidistance. Okay, so we would know here that also BD and AD are equal to each other because of this perpendicular bisector theorem, in addition to all the other letters that I could add. Okay, so that's one of the theorems. I'll even highlight this because this is a new theorem that's on your yellow sheet that we're going to see on the next page as well. Okay, so again, without doing the entire proof, same with number 2 here, where you're given this time that segment AD is perpendicular to segment BC. So again, you would have right angles. So we see right angles, we'd have another reflexive property because AB and AC are congruent already. This one is not SAS. Instead, this is an RHL because SSA is not possible. So we know we would do this one using RHL with the reflexive. We would have to show I have right triangles, and then from there, you could say that these triangles are congruent by RHL. But look at what we're trying to prove. We're trying to show that angle B and C are congruent, and so they are part of the triangles I'm trying to prove. So right after RHL, I'll have one extra step that would say if triangles congruent, then all their corresponding parts are congruent, and that would give me angle B and C are congruent to each other. Like we're trying to say these two are congruent. I did them in a different color just because that's what we need to show. We still need to show that that's the case. Once we know the triangles are congruent, we would show that. Okay, so again, I'm not going to do the entire proof. If you want to try it out though, this comes out to 6 steps. It's really not too bad because it just kind of uses RHL where you already know the hypotenuse are congruent. You just need the reflexive side, and actually I should do this in a different color to show that I don't know it just yet. You do the reflexive, you show that you have right triangles, and then you can do RHL and finally finish up with B and C being congruent. So this theorem is called the base angles theorem. And you write that on the yellow sheet. So the yellow sheet does not use these like names of the theorems, like this one was perpendicular bisector, this one's called base angles theorem. Instead, it uses like an easier way to know what the theorem is telling us. So this is what it writes. It says if, and it draws a triangle, and on that triangle it gives these legs are congruent. Okay, so it's telling us that if you have a triangle which has legs congruent, notice on this original triangle, this whole thing here, the big triangle here, ignore the middle that's kind of drawn in. We're saying if these are congruent, then the base angles are going to be congruent. These guys down here. The base angles always touch the actual legs at the base. They're not, the other angle is called a vertex angle. We don't know anything about that angle, but this is the base angles theorem. Okay, and again, I'm going to highlight this one because it is a new theorem that we're seeing today. And it's on the next page as well. This is just kind of getting ready for that theorem. And finally, the last one deals with kind of like the converse of the base angles theorem that we're about to see, because it shows us that if you have, again, another perpendicular, AD is perpendicular to BC, you have some right angles again that we're going to show, with the reflexive again that we're going to show, and this time you know these angles, and actually I'm going to do that in a different color because we already know they're congruent. We're trying to show the stuff in orange is going to be congruent, and then this would be an AAS. So once you show AAS on this one, you would be able to show that these triangles are congruent to each other, and then you could use all the corresponding parts to help you show that segment AB and segment AC. So if I did that in a different color here, I want to show that these are congruent. Oops, and I just need one tick mark on that. So I would need to show this. Okay, so then you could do the proof again. It comes out to about 6 steps, I believe. Yep, 6 steps on this one as well. And once you're done with it, we would have proven this theorem, which is the converse to the base angles theorem. So it's converse of the one we just talked about above, which says, and this is the shorthand now, I'm going to draw this picture similar to this. It's on our yellow sheet, and again, I'll show you where that is on the next page. It's going to say if triangle, and we're going to draw these little base angles that are congruent, then, and you draw the triangle with the legs congruent. And again, this is just talking about one triangle. It's talking about an isosceles triangle. That's what this is referring to. Because isosceles triangles have 2 legs the same, which means 2 of the base angles are the same. Okay, and then I'm going to highlight this last one. And these are the 3 new theorems that we're about to see on the next page. Okay, so let's go to the back. We're going to fill out the theorems again, just in detail so that you know exactly each of them. The only ones that we didn't talk about yet is what happens with like equilateral triangles. We're going to see that as well. And then we'll practice a little bit on the bottom. And so it helps to have the yellow sheet. I'll show you where everything is on this sheet. So if you go to the back here, the first theorem we do start off with is the perpendicular bisector theorem, which says in a plane, if a point is on the perpendicular bisector of a segment, then, and then this is the rest of that theorem, again, just like we wrote on the front, then the point is equidistant from the endpoints of the segment. Which means looking at this diagram, if we knew that point C is on the perpendicular bisector CP, that's the line CP, then I know then that A to C is equal to B to C. So as a result, we know this is true. AC is equal to BC. You have enough information based on knowing that both you have a perpendicular and you have a bisector. It's being bisected and it's perpendicular, and that's how we know AC is equal to BC. That's what this theorem says. And again, here it is on the yellow sheet, just because I showed you, did tell you I was going to show you that. It says if perpendicular bisector, whoops, not that one. We're down here. We're on if point on perpendicular bisector, then the point is equidistant from the endpoints of the segment. And its converse is also there after that. We don't have the converse written down here. We don't use it as often, but you could always use the converse as well to show that there's something on the perpendicular bisector. Now, if you're wondering why are these first two here that we didn't talk about at all, those are actually the definition for perpendicular bisector. So this is perpendicular bisector definition, because look at the word definition here, whereas this is a theorem that you're looking carefully at. This is a perpendicular bisector theorem. It's just something that's true about perpendicular bisectors, whereas this is the actual definition. What makes something perpendicular bisector? It has to have both these things true. Now, we don't often use the first two in a proof as often, but we can to help us use the theorem then later. Okay, so then we have the base angles theorem, which says if two sides of a triangle are congruent, like notice it's an isosceles triangle, then the base angles are congruent. Okay, and then we would know then that angle A in this diagram is congruent to angle C. Those are the base angles. Whereas B is the vertex angle. I don't know anything about that one. Here's what it says on your yellow sheet again, and I'll show you this in a second. If, and it shows that triangle with the two tick marks there showing that it's isosceles, then it's going to draw the triangle with the two congruent rings around it for the base angles. Okay, this is what I wrote on the front page, and I highlighted it already, but just to write it one more time to make sure you know that that's the new one on your yellow sheet. Here it is. And it's hard to see if the picture didn't print out as great. You can add in little tick marks on those if you don't quite see them. There's a tick mark here and here, and then there's these little rings at the bottom. And then we're about to do the converse, which basically shows the little rings and then marks the tick marks onto the actual legs. And then we'll finish up with the last two. So this one says if two angles of a triangle are congruent, then the legs are, that correspond are congruent. And then those two legs looking at this diagram would be RP is congruent to RQ. Right? You can tell those would be the two sides right here. And let's go ahead and write down again the theorem here. If and I'm drawing the triangle with the base angles congruent this time, and then I'm saying that the legs would be congruent, the legs that correspond to them. Okay, and again, this is on your yellow sheet. I just showed you that it was the converse that we're working with. Okay, so it's the converse of the base angles theorem. Then we have two new ones that we didn't mention on the front page because it was like more of an extension of base angles theorem. It talks about this thing called a corollary. A corollary is just like more explanation of base angles theorem. So not only is it true for isosceles, now it's talking about an equilateral triangle, which we already know a lot about equilateral triangles. We know that they're already, if a triangle is equilateral, then it's also equiangular. That means here's the shortcut way of writing this. Instead of using all those words, you can just draw a diagram and show that if three sides of that triangle are congruent to each other, then three of the angles would all be congruent to each other. And if you apply this information to already knowing about the triangle sum theorem, you're going to know that all three of these angles are 60-degree angles. And not only are they all congruent to each other, they are also equal. Measure of angles are equal to 60 degrees. Okay, so R, S, and T would be congruent to each other in this diagram. Whereas if we talked about the triangle being equiangular, then it's going to end up being equilateral. And then we can draw, again, another diagram just reversing that, showing that these three angles are all congruent to each other. Therefore, the three sides will be congruent to each other. Okay, so if I highlight both of these are actually on your yellow sheet as well. I'll show you where they're the last two of all of unit 4 that's on our yellow sheet. But we don't use them as often, and it's hard to see the little tick marks, so if you can't quite see them, there's 3 tick marks on this one and 3 little rings around the triangles, whereas the last one shows 3 little rings around the triangle and 3 tick marks on the last part. Okay, so if you don't quite see what's there, you can always kind of write them in darker. We don't use them as frequently as we probably could, but they will come up occasionally. Okay, and these are all theorems that we just saw. So what we're about to do now is, and actually this part, we also know that segment GH is congruent to segment HI is congruent to segment IG. Right, because all 3 of those sides would be the same. Okay, so now that we've seen 5 theorems today. The first was the perpendicular bisector theorem, which we could have looked at its converse if we wanted to as well. And we did the base angles theorem and its converse. We did the corollary to the base angles theorem and its converse. So now we're just going to apply them into these problems where it says, like, here, can you find the values of x and y using the different theorems? Could you, and so on, and we'll kind of practice them. So the first one just says, can you find the values of x and y? Don't forget about the stuff you already know about triangles, which is the triangle sum theorem tells me that all of the angles add up to 180 already. And notice I have a right triangle somewhere right there too. So let me zoom this in a little and we can work through this. So first thing I notice is a bunch of tick marks. If you see that in this triangle here, I have 3 tick marks, that means all 3 of my angles have to be the same. So I have an equilateral or an equiangular triangle on this one. So all of these angles are 60 degrees. Okay, because 180 divided by 3 tells me that each of the angles is 60. Should know that piece whenever you're working with equilateral or equiangular triangles. Well, if this part is 60, and it shows me that this whole thing is a right angle, then this portion right here is then 30 degrees, because 60 plus 30 would get me that 90 degrees. So you know what 4x minus 2 is equal to. It would have to be equal to 30 degrees, not 90, because the whole thing is 90. It's just pointing to that little 30-degree angle part. And we could solve this to find x. So you have 4x equals 32. X would equal 8 once you divide by 4 if you need it. Okay, so we found x. We're halfway there. We need to find y still, so let's keep working through this diagram. Next, you hopefully notice that this triangle, I'm outlining it in green here, is an isosceles triangle. An isosceles triangle because we see these little tick marks here. That means then that we know these base angles are congruent to each other. Well, if that was 30 degrees, then so is this. Okay, so we have 2 30-degree angles here. It also makes sense that this would be 120 degrees because it's a linear pair, and that's going to be 180, and that leaves you with 60 degrees left over for these two. Now, they didn't have to be the same unless they were isosceles, which they are. That's how we know they're 30 and 30. So now I want to do 7y plus 9 equals 30 and solve for y. So this ends up being 7y equals 21, and dividing by 7 gets you y equals 3. Okay, so we found our x, we found our y. Some of the homework tonight is going to have you practicing things like this, and you'll definitely see something like this on the quiz as well. Okay, let's move over to number 2. It says 3 points here. L, O, and Q are collinear. So even though you can't see them connected, we could connect this with a line. That's why I'm going to go ahead and just connect it so you can kind of see it that way now. It says find X if it's possible, and if it's not possible, then write the words not possible. Let's see if it is possible or not. It has to deal with the diagram, and we can tell already that we have a right angle here. And our goal is, do we have enough information to know that are they congruent to each other? Or do we have like a perpendicular bisector? Because if we do have a perpendicular bisector, then we'll know which segments are equal. So let's say, because you know this, 15 and 15 here, these two are equidistant. So like, even though segment LM is congruent to segment LP, we also know that LM is equal to LP, right? And if LM is equal to LP, this would be the converse of the perpendicular bisector theorem that says if, and let me show you where it is in case you're wondering, it says if point equidistant from endpoints of the segment, then the point is on the perpendicular bisector. So since LM and LP were equal to each other, that means that point L is equidistant. I'm writing a lot of detail here. You wouldn't have to do all of this, but I'm just making sure it's clear. Point L is equidistant to M and P. So therefore, it is on the perpendicular bisector. And that means then that the perpendicular bisector would be line L, the one that's QO is kind of the perpendicular bisector, or you can extend that whole line if you want to and call it LQ even, whatever way you'd like to call it. QO or LQ is the perpendicular bisector. And so as a result then, since Q is also a point on the perpendicular bisector, then it's got to be equidistant to the endpoints M and P. And so that's how I know that MQ would be congruent to PQ, or that MQ would be equal to PQ, and I could then set them equal to each other and solve. So I could do 4x plus 3 is equal to 11 and find x. So this one was possible. Specifically, it was because of the perpendicular bisector theorem, the converse of it first, to find out that L was on the perpendicular bisector. And you can call the perpendicular bisector QO, or even LQ, or you could call it LO. It's really, there's so many ways to name this. OL, so on. Those are all ways to name the perpendicular bisector. But once I solved it here, set them equal to each other, and I solved by subtracting 3 divided by 4, you should get x's 2. Okay, and that's where we're going to stop here. If you have questions, just bring them with you tomorrow. Homework tonight is 4.9, so go ahead and try out that 4.9 homework in the same packet you had yesterday.